In our final problem, we have a 4-bar mechanism. This is a slider crank mechanism. There's one revolute joint right at point O, another revolute joint at B, another revolute joint at C, and then this bar BD is sliding inside this collar, and then as a result of this BD is rotating about point C, and this collar is rotating with BD. Then we are given some information about the motion of this mechanism. OB rotates clockwise direction. This is the direction shown over here in the clockwise direction by 5 radians per second. It's a constant rate. That means alpha O would be equal to 0 in that sense. Then at the instant where the state angle we find from this axis is 90 degrees, so OB is aligned in the vertical direction like this. This is point D, in that sense. At this instant, we are asked to determine the angular acceleration alpha of the rod BD. There's our rod BD, and as it is rotating with the collar, what is being asked is actually the angular acceleration of this collar as well. So it's basically can be interpreted as the angular acceleration of this rod BD or the collar that is rotating about point C. Now, the information that we have in this question leads us to a couple of solution directions. One direction is that we already know the speed and the acceleration of this bar, the angular speed and angular acceleration. That means we can calculate the speed and the velocity and the acceleration vectors of point B, and point B is actually a part of this BD bar. So we know we will be able to calculate the velocity and acceleration of a point on this bar. So for another point, then we can write out an equation based on our rigid body kinematics. Then what happens about this collar is that this collar is rotating. So there is a rotating frame here, and we can choose this frame in this way. For example, X and Y. And then, relative to this collar, this bar BD has a relative motion. This relative motion is not about rotation, but it's a straight path motion. So it is moving back and forth, inside and out of this collar. So it's moving in the X direction in that sense. There's a motion of this BD in the X direction. So I can write out another equation based on this interaction of this color and then this link BD. And for sure, the motion will be in the X direction. So if I'm going to write out a V relative for this part, then it will be a sum V relative in the I direction based on my selection of this frame. And A relative will be in a similar way. It will be in the I direction for sure. So it's a good idea to start writing my equations by making use of this frame, because B relative and A relative will not have a component in the Y direction, and that might be helpful in finding solutions for this problem. So this is my selection. There's the X direction, and the relative motion of this link BD with respect to the color is in X direction always. And they are rotating with the color about point C. So we can start out by writing our equation, and remember that when we are writing out these relative motion based on the rotating frame motion, we have these terms like the Coriolis Coriolis acceleration, like omega cross product V relative. Also, we have the centripetal part as omega cross product, uh, whatever the R is there. So, and then we have a term as alpha cross product R. Actually, alpha is something that we are looking for here. So this is going to be what we are trying to find. But we don't know omega as well. We don't have any information about the angular velocity of this part. So probably it's a better idea to start working in the velocity domain first and then find out this information for v relative, find the information about omega, which will be useful at the end in our relative motion with respect to rotating axis equation. So having that in mind, we can start our solution stating that the angular velocity of the color is actually should be equal to the angular velocity of the BD link, and it goes the same way for the angular acceleration. They should be the same. We can write out the equation for the velocity analysis of rotating frames. Velocity of A equals to velocity of C plus velocity of A with respect to C. But since the frame on C is rotating, there's this omega information, and there's this CA vector and V relative. Now, at that instant, the A point that we define is the point right on C. It's a point on BD. However, it is at that instant of time coincident with point C. So therefore, its distance vector, CA vector, becomes equal to 0. And then velocity of C, as it's a fixed location, is equal to 0. And we result in saying that velocity of A point is equal to the relative velocity defined, which is V relative in the I direction. We could have actually written out the equation for a different point around here, but it wouldn't give us any more information. What we got here is that velocity of A point, and it's a point on the rigid body, is equal to V relative. Why is that important? Because we already know a velocity of a point on this rigid body, velocity of V. How do I calculate that? Omega 0 times this radius would give me the velocity information, right? So it's quite easy to calculate. It will be just equal to omega 0 cross product or V vector, whatever the instant is. So we need to obviously use the same type of notation here. Omega 0 is in the k direction, and the way that it is defined here, z is going out of the board, omega 0 is in the negative sense in that case. So if we are going to write out this equation, this is the way to write it out. Negative omega 0 k. Okay. Then OB will be, although OB is in this way, it is in the vertical direction, we are going to resolve it in the xy axis. So we need to find out the angle at that instant. So let's go back here. VA can actually be calculated by using VB. This is the rigid body equation. Remember, 2 points on the same rigid body. A and B points are on the same rigid body. And then there's this omega cross product BA. Omega is something we don't know. BA is something that we can calculate. Actually, BA information is from B to A point or B to C point at that instant of time. So we need to go back to our geometry. And on the geometry, what we have is the crank link's length. This is 0.25. This is the crank link's length. It's in the vertical direction. 0.6 is the location, fixed location of C with respect to point O. And at that instant, we know that this is 90 degrees. This is 90 degrees at that instant. So we can calculate this beta angle. And also we can resolve this VB in terms of x and y. This is the x-axis. This is the y-axis, right? So in terms of this x and y, velocity of B would be resolved by these two vectors. Positive in the x direction, negative in the y direction. So based on that, first of all, velocity of B is calculated by using this omega 0 information. This is 0.25 omega 0, and the direction is shown here as the rotation is in the clockwise direction. It is 1.25. This is just a magnitude. We don't have any sign here. And on top of that, now we know about the resolution of that. We're going to use this beta angle. So beta angle should be calculated by these lengths of 0.25 and 0.6. It is calculated as 22.6. And BA length is calculated based on this trigonometric equation. And this is point B, this is point A, and this is our axis XY. From B to A, we move in the negative direction of X. That's why we have a negative sign right over here, negative I direction, and this is the magnitude of that from our trigonometry. Then velocity of B is calculated by using this magnitude of the velocity, and its resolution is based on this beta angle. This is the beta angle, by the way, shown here. That's the beta angle. Cosine of that will be in the x direction. Sine of that will be in the negative I direction, negative j direction, sorry, negative y direction or negative j direction. So cosine beta in the positive I direction, sine beta in the negative j direction, and this is the resolution of the velocity of B point with respect to our selected plane. Now we have enough information to relate these two. Velocity of A was calculated as V relative, which is something we don't know, and then there's our information about the velocity of A calculated with respect to velocity of B. Velocity of B is first calculated. That information appears right here. Oops. Okay, that information appears right over here. Then this is the extra term omega K, cross product BA vector. Omega again is something we don't know. But when we take a look at this equation, this V relative is in the I direction. Let's do the calculation here. K cross product I is J. So omega appears in the J equation. That means from this vector equation, we get two scalar equations in X and Y axes. From the X-axis equation, we will be able to solve the V relative. From the Y-axis equation, we will be able to solve omega. We need both of